Welcome back. All that math we did last time was worth it, because now we're going to be able to analyze all kinds of interesting op-amp circuits without having to do a lot of math, because we understand those two simple rules that govern the behavior of op-amps. Namely that there's no current flowing into their inputs, and with negative feedback, the two inputs, the plus input, the non-inverting input, and the minus input, the inverting input, have to be at the same voltage. The negative feedback guarantees that, and it will keep things that way. So let's plunge into the first of several lectures in which we look at increasingly complex circuits involving op-amps and circuits that do other things than simply amplify. So I'm going to begin by looking at the circuit we had last time, the simple inverting amplifier, and I'm going to analyze it again using the op-amp rules. But no math alert this time, because it's very straightforward. And I'm doing this because I want to show you how simple the op-amp rules make it to analyze circuits involving op-amps, and then we'll use the rules in the same way to develop other circuits. So here again is our inverting amplifier, an op-amp, an input resistor Rin, a feedback resistor RF, but now we know the op-amp rules. Remember where they came from. They came from doing all that complicated math, but we never have to do it again. The op-amp rules came from doing the complicated math and then making the assumption that the gain A, the intrinsic gain of that triangle, the intrinsic gain of the op-amp, was much, much bigger than 1. That gave us rule 2, that V plus is equal to V minus. It also helped us with rule 1, although rule 1 is also a feature of the op-amps and the way they're designed. So let's see if we can understand how to apply these rules to our inverting amplifier, and in a very short time get the same result we got last time with much more complicated steps. So rule 2 tells us that the inverting input and the non-inverting input are at the same voltage. We've forced the non-inverting input to be at ground, 0 volts, and that means the inverting input is also at effectively 0 volts. We saw that very tiny variation last time, essentially 0 volts, down in the millivolt range or lower. So effectively, rule 2 tells us that the negative input is as if it were at ground. Once again, it's not really connected to ground, and that's important for the workings of the circuit. But as far as that input resistor and whatever's connected to the other end of it, on the other side of the input resistor is ground. Not really, but that's what the circuit acts like. So rule 2 tells us that V minus is 0. We've got a virtual ground there. So the input voltage thinks it's just applied across a resistor, the other end of which is grounded. And so Ohm's law tells us that the current is simply V in over R in, because we got V in on one side and 0 on the other side. The voltage across the resistor is simply V in. Ohm's law, I is V in over R in. Now we go to rule 1. Rule 1 tells us, well, that's not quite what it says, that's what it infers. Rule 1 says no current flows into the op-amp inputs. That means this current we've drawn that's flowing through Rin can't go into the op-amp through its input. The only place it can go then is through RF. So our inference is from rule 1 that I goes through RF. There it goes. Same current that came in is on its way through the feedback resistor. What happens to it after that, if you're wondering? Well, some of it might go to the output if there's other stuff connected there. The op-amp's transistors will sink it in and eventually deliver it back to the ground and the power supplies and so on. So the op-amp is doing its magic to make this happen. Ohm's law tells us if I have 0 volts here, and I've got a current I flowing through RF, I've got a voltage drop across RF of I times RF, and this side is more positive than this side. But this side's at 0, because that's the way the current's flowing. This side's at 0, so this side is negative. And it's negative by 0 minus the current times the feedback resistor, so V out is 0 minus I RF, and that's simply minus I RF, because 0 minus I RF is minus I RF. But we used Ohm's law to figure out I. So V out is minus V in over R in, that's the current, times RF. And if we rearrange that, it's simply the ratio of the feedback resistor to the input resistor times V in. And it is a negative gain, a gain RF over R in, but negative RF over R in, because we are coming into the inverting amplifier. So there is a way of developing the inverting amplifier very, very, very quickly using the two op-amp rules. And we will analyze all subsequent op-amp circuits, even much more complicated ones, basically by applying the op-amp rules. We can also make complicated circuits by building up different renditions of this particular circuit. Before we do that, I want to say a few things about this inverting amplifier circuit in this particular configuration. First of all, the feedback enhances the 0 volts at that virtual ground, as I said last time, because with that voltage at almost 0, there's no incentive for current to go into the op-amp even if it didn't have a big input resistance. So that's one nice aspect of this. On the other hand, remember, an amplifier would like to have a big input resistance. Well, the op-amp does, but this whole circuit is the amplifier we've now built. And in this configuration, there's typically significant current flowing at the input. We had a 10 kilo ohm resistor there, for example, in the circuit we built in the previous lecture. So one disadvantage of this circuit is that it doesn't really provide very, very high input resistances. And if you had to make this input resistance, if you needed to make it 100 kilo ohms and you wanted a gain of 10, that would need to be 1,000,000 ohms, and that's beginning to get a little too big for this op-amp, comparable to the intrinsic resistances inside it. So you can't really use the inverting amplifier configuration to make an amplifier that has a very large input resistance. Now, in many cases, that's not a problem, but it could be. The other problem with the inverting amplifier, might be a problem in some applications, is it's an inverting amplifier and you might not want it to invert. Well, how do you solve that problem? Well, you solve that problem by adding another stage of inversion. Two negatives make a positive. And so let's look at a very simple circuit that does that. Here I have a two-stage non-inverting amplifier. Two stages because I got two op-amp stages. The first one, if you look at it, has a 10 kilo ohm input resistor and a 30 kilo ohm feedback resistor. So that's a gain of -3. The output of that one goes into a 10 kilo ohm input resistor of another op-amp in exactly the same inverting configuration. This one's got a 10 kilo ohm feedback resistor too. So I don't want to say it has no gain because it doesn't have zero gain. It doesn't give 0 at the output. It has unity gain, we say. It has a gain of 1. The output is equal to the input, but it's a gain of -1 because it's the inverting configuration. And so that second amplifier simply inverts the output of the first amplifier. We had -3 for the gain of the first amplifier, -1 for the gain of the second amplifier. And so this whole two-stage non-inverting amplifier that I've constructed here has a gain of +3. And there is the output from Do Circuits oscilloscope that you can actually put a simulated oscilloscope, connect it to your circuit and Do Circuits, and there it is, and you see in the red curve the input, and you see the output is in phase with it. That is, they peak together, it's not inverting, and you see that the output is 3 times the input. And so we have a two-stage non-inverting amplifier with a gain of 3, a gain of +3, which is the same as saying it's not inverting. Well, let's take a look at the real thing instead of just looking at things we can do in simulation or by drawing circuit diagrams. And what you see is a couple of op-amps. There's the first one. That's the very same op-amp we used in the previous lecture. I've just changed the resistors a little bit. I've got a 10 kilo ohm resistor at the input, and the closest I could get in the standard resistor values was a 33 kilo ohm, so this is more like a gain of 3.3. By the way, later on, we'll be working with some very precision resistors you can buy that are good to 1%. And then I could have bought a 10K and a 20K or a 10K and a 30K, but I'm using just standard resistors here. So here's the op-amp. The output of the op-amp is over here. The output goes back through that 33 kilo ohm feedback resistor to the input to that first op-amp. The input resistor feeds in, and here's the input signal coming in from our function generator. This time it's a 1 kilohertz signal. The input resistor and the feedback resistor join at the inverting input of the first op-amp. The output not only goes back to the input through the feedback resistor, there's the negative feedback, but it also goes into the inverting input of the second op-amp through that other 10K resistor, and then there's a 10K feedback resistor, and the output of the second op-amp is over here. Well, right now, we're looking on the big screen at the input to the circuit and the output of the first op-amp, which we see is an inverting amplifier Where that's trough, that's a peak. Where that's a trough, that's a peak. It's an inverting amplifier with a gain of about 3. These both are on 2 volts per division, so that they're in the same scale, and that's about 3 times the amplitude of that one. And so we've got a gain of 3 inverting amplifier in our first stage. Now let me just move the oscilloscope probe to the output of the second stage. And lo and behold, we've now, whoops, that's a problem. Okay? Now, this is a good educational point. I didn't mean that to happen, but let's go on with it. What on earth is going on? Well, I can see what's going on. I can see that the output of the second amplifier is not doing what it's supposed to be doing. In fact, if you look at it, it's swinging up to some very large value, which is in fact at 2 volts per division, about 2, 4, 6, 8, 10, about 12 volts. Oh, that looks like it's close to the op-amp's limit, and it's going down to about -10. So somehow this op-amp is not in control. The feedback isn't working, and the chances are what's happened is the feedback resistor has somehow become disconnected. So let's see if I can fix that and get that feedback resistor back in there. The common problem when you're working with and there it is. I had a bad connection at the feedback resistor, and when I connected the probe, it pulled it out of the little connector in that board. So we fixed it, and now we have a gain of 3 times that, and it is non-inverting, peak here, trough here, trough here. So you want a gain of 3 non-inverting amplifier? There it is. Make it out of 2 inverting amplifiers, one with a gain of 3, and the other with a gain of -3, the other with a gain of -1. Okay, so that's what we did. Works great. We could have, by the way, had a gain of the square root of 3 in each amplifier if we had wanted, and we still would have come out with 3, but I chose to make a gain of 3 and a gain of 1, gain of -3 actually, and a gain of -1. So there is a simple embellishment on our idea of inverting amplifiers. Let's move on and look at some other amplifiers we can develop here with these circuits. So let us take a look now at a slightly more complicated situation, a situation in which we're going to talk about an amplifier that's going to have 2 inputs. Let's see what we get. So here is an amplifier called a summing amplifier, but it's not a summing amplifier yet. It's simply the same inverting amplifier we've just been talking about. I've drawn it with an input voltage. I'm calling it in1 this time because we're going to have 2 inputs. There's an input current. I'm calling I1. The current is flowing to virtual ground. It isn't really flowing to ground. It's going through the feedback resistor. But as far as that input resistor is concerned, its right end is basically connected to 0 volts to ground. And now here's the beauty of this situation. I can connect a second input resistor with a second input voltage, input number 2, to that same point, that virtual ground point. And the reason for that point is sometimes also called the summing point. Because what happens at that point is currents that are coming in through those 2 resistors all think that they're going right to ground. So they don't know anything about the other currents that are flowing in the other resistors, and they become completely independent of each other. That wouldn't be true if that point weren't virtual ground, but were connected to ground through yet another resistor, because the voltage drop across that resistor would be determined by both currents and so on. It would affect the currents through each resistor. But because of that virtual ground, each of these resistors just thinks it's connected to ground on the right-hand side. And the current that flows in I1 and the current that flows in I2, according to op-amp rule number 1, no current can flow into the op-amp. So both those currents together flow through the feedback resistor. And the current in the feedback resistor is the sum of the 2 currents coming in through those 2 resistors. So we have what's called a summing amplifier, and let's work out in a little bit more detail. V out, well, what is V out? Just as in our simple analysis before, we've got that virtual ground at the inverting input, 0 volts. We've got a drop now of I1 plus I2 times the feedback resistor across the feedback resistor. The left-hand side is 0, so the right-hand side, which is V out, is minus I1 plus I2 times the feedback resistor. Now, what are I1 and I2? Well, they are V1 over R in and V2 over R in. For now, I've given those 2 resistors, the input resistors, the same value. So if I take those quantities, V1 over R in, the lower resistor R in, V2 over R in, the upper resistor is also R in, and I plug them in for the I's there, and I work things out, I get that V out is minus the sum of V1 and V2 multiplied by this factor, R feedback over R in. So this is a summing amplifier. It's an inverting summing amplifier. Its output is basically the sum of the input voltages, negated, inverted, and then multiplied by this gain factor, RF over R in. So we can build a summing amplifier. I mentioned earlier that op amps are called op amps partly because they do mathematical operations. Well, here's an op amp doing a mathematical operation. It's adding two voltages, and the output is basically the sum. If you don't like it to be the negative sum, put a unity gain inverter on the back of it, just like we did with the gain of 3 amplifier before. If you don't want it to change the voltage, but actually simply add them, make R feedback equal to R in, and you will get an output voltage whose magnitude is the sum of the input voltages. So this is a summing amplifier, and very useful circuit, and it works because we have this virtual ground at the minus input of the op amp, which means that the two currents can flow independently without either one knowing what the other one is doing. And before we move on and actually look at one of these amplifiers in the flesh, as it were, let's look at two other possibilities. Let's first of all look at what we could do if we didn't want an actual sum. We wanted to weight the sum. We wanted one input to count more than the other. Well, then we could take the input resistors and make them different. And then I1 would be V1 over whatever R1 was, and I2 would be V2 over whatever R2 was, and when we put those in, we get a weighted sum, weighted by those two different resistors, weighted by two different gains. And so we don't have to simply add the inputs, we can add them and give them different weights if we want. And to see if you've got this whole concept, and that's a lot coming at you pretty fast, let me give you a quick quiz. So here's a circuit in which I have an inverting summing amplifier at the beginning. It's got a 10 kilo ohm input resistor for V1. It's got a 15 kilo ohm resistor for V2. It's got a 30 kilo ohm feedback resistor, and then it flips into a unity gain inverter. What's V out in terms of V1 and V2? Press your pause button and figure this out, and we'll come back and look at it. Okay, well, here we have what input 1 sees. It sees 10 kilo ohms and 30 kilo ohms, so it basically has a gain of 3. Let's look at the other two resistors. The V2 resistor is 15 kilo ohms. It goes to the same 30 kilo ohm feedback resistor. That's a gain of 2, or rather minus 2. And then we have the unity gain inverter. So before we get into the unity gain inverter, we've got minus 3V1 plus 2V2. We invert that with the unity gain inverter that doesn't change values, but just changes the basically the sign. So there's the unity gain inverter, and V out is 3V1 plus 2V2. Okay, well, let's take a look at what this circuit does. First, if you'd like to have a little bit of lab time, you could actually simulate, say, a gain of 2 summing amplifier that weights both inputs equally. Do it in your circuit simulator and verify that it works. And we'll use inputs of 1 volt and 2 volts, and then replace them with sine waves at slightly different frequencies and see what you get. And I've suggested some parameters. If you're using Circuit Lab, Do Circuits usually defaults to parameters that will work for this. And I'd like you to describe how the output would sound. If you don't want to do this lab time, don't bother. But if you do want to do it, pause, do the lab, and let's come back and look at what we get for results from this. So here are the results. On the left, I'm doing DC results. I've got 1 volt at V1 and 2 volts at V2. The output is supposed to be a summing amplifier, an inverting summing amplifier that weights the two equally, and indeed has a gain of 2 here. And so indeed we have 1 volt plus 2 volts is 3 volts. Double that, you get 6 volts. Invert it, you get minus 6 volts. And that's indeed what the voltmeter reads. In the case of the AC, things get very interesting. I've got an input voltage sine wave at one frequency and a sine wave at a slightly different frequency. And when the troughs line up, they cancel each other. And when the crests line up, they reinforce. And the closer the two sine waves are in frequency, the longer you have to wait till they come into phase or go out of phase. You see the output of Circuit Lab's graphing showing what that pattern looks like. And I'm asking you to imagine what that would sound like. Well, I'm going to play you that sound not for the frequencies shown here, but for a case where they're even closer, a 440 hertz sound and a 442 hertz sound. And here's what they sound like. And what you're hearing is the phenomenon called beats, in which these two very close frequencies come into synchronism and then go out again and in and out, and you see a very slowly varying intensity of sound, varying at roughly the difference frequency of those two waveforms, which is just 2 hertz. So one interesting example of what you can do with a summing amplifier, we're summing two waveforms that are slightly different. By the way, you may remember that I've used my function generator on several occasions to add a couple of signals, to add, for instance, noise to a sine wave when I wanted to demonstrate a filter. Well, what the function generator has in it is a summing amplifier that can be switched in at its output, and it has two different channels that can generate two different waveforms, and you can use those two different waveforms to add them. You can use the summing amplifier to add them, and then you get that output, which is the sum, and in this case, this is an example. Okay, well, that's several examples of circuits we can make with op amps. I want to go and show you one other circuit which is somewhat similar to, but not exactly the same as the circuits we've built already, and then we'll actually use it to end by building a really useful circuit. So here's another use of the inverting configuration. Sometimes you have not a sensor or an input signal that is a voltage, but something that actually produces a current. One example is a transistor, because the collector circuit of a transistor produces a current that depends on the base circuit. There are many other sensors that produce a current. But you'd like to be able to read that current with some kind of easy-to-read meter, like a voltmeter. So you need a current-to-voltage converter. And a current-to-voltage converter is even simpler than the kinds of circuits we've been dealing with already. So what this circuit shows you on the left is a circle with an arrow in it that represents a current source. It shows you that that source is going to provide current flowing in the direction shown. And we're going to apply the op-amp rules. So the op-amp rules say with negative feedback, V minus is equal to V plus. And we've got a feedback resistor there, so we've got negative feedback. So that means the negative input, the inverting input of the op-amp, is at virtual ground. So that's the current source is very happy. It's happy to pump its current, it thinks, to ground. But rule 1 says it doesn't really go to ground. It goes through the feedback resistor. Same current going through the feedback resistor and around, and then to the output or back into the input of the op-amp, into the output of the op-amp or out to some external circuit. The op-amp takes care of all that. But there's what happens. And just as with the analyses we've been doing before for the voltage amplifiers, we can say the output is minus I times the feedback resistor, because the left-hand side of the feedback resistor is at 0 volts. There's a current I flowing through it, and that current I is multiplied by the feedback resistance to get the voltage across the feedback resistor. So V out is minus I in times RF. So a current-to-voltage converter is like one of these inverting amplifiers we've been building, except it doesn't even have an input resistor, because it is getting a current at its input directly rather than a voltage, which, if you will, produces a current through the input resistor. So it's even simpler. And let me now reconfigure my setup a little bit and show you a very practical application for a current-to-voltage converter. Okay, so here is a practical application for that current-to-voltage converter that I just discussed. It looks pretty similar to that circuit, except instead of that arbitrary current source, I've got some particular practical device, and I need to talk a little bit about that device so you can understand what it does. On the left is a phototransistor. Now, what's a phototransistor? Well, if you look at this device, it looks sort of like a transistor. It's got a collector, it's got an emitter. Does it have a base? Well, yes, it has a base, but it's got no connection to that base. And instead, it's got a couple of arrows coming in. They look like the arrows we use to talk about a light-emitting diode. They were the light going out. Well, this is light coming into the phototransistor. What a phototransistor does is it uses light to produce electron-hole pairs at the base. And when you connect a voltage to its collector, this is an NPN phototransistor, similar to the NPN transistors we've been using, you will get a current that depends not on a base current, because there's no connector to the base, but depends rather on the intensity of the light falling on that base. These transistors are built in transparent plastic cases. That base is exposed to light, and when light falls on it, the energy of the light creates electron hole pairs. It's very similar in some ways to the operation of a photovoltaic cell, although a PV cell is just a diode, and this is a little more complicated because it's a transistor. Well, that transistor produces a current that's dependent on the intensity of the incoming light. And now we take that current and we run it into a current to voltage converter. So here comes the current, which is proportional to the amount of light, the light intensity. That current, by the op-amp rules, can't flow into the op-amp, so it flows through the feedback resistor, where it causes a voltage drop across the feedback resistor. So the right-hand end of the feedback resistor is at a lower voltage than the left-hand end. The left-hand end is at 0 volts by op-amp rule number 2, because that says with negative feedback, which we have because of the feedback resistor, the two inputs, the inverting and non-inverting input of the op-amp, will be at the same voltage. And that, in this configuration, where the plus input is grounded, gives us a virtual ground at the inverting input. So same configuration as the inverting amplifiers we've been building, same configuration as the current to voltage converter. In fact, this is the current to voltage converter, except our current source is now a light sensitive, a light intensity current source that produces a current proportional to the light intensity. And so we get at the output an output voltage which is proportional to the light intensity. Now, with the circuit hooked up as I've shown it here, we would get a negative voltage for current flowing down in the direction I've shown here. So I'm going to go to a circuit which is very similar, but I want to tell you a few differences in this circuit. The main difference is I would like to do something which I think is really silly in this digital age, but to me it makes sense. There are times when I really like to see an analog needle move to show me what's happening in a circuit, especially when changes are occurring. It's a little harder to grasp the changes when you're looking at a digital display, especially because a digital display is usually bobbling around in the last few digits as things vary slightly, and you miss the point that the big variations are what you want to look at. So rather than hook up my fancy digital voltmeters, I've taken a very old-fashioned analog voltmeter here, and I've connected it to the output of this circuit. So now I have a way of reading the light intensity, that is the output voltage of the op-amp. The other difference is, because this voltmeter reads only positive, well, I could have switched the leads, but that would have looked confusing. So because it reads positive, I've actually turned the phototransistor around, so it's going the other way. I've connected the emitter at the top, and I've connected that to minus 15 volts, in fact, and I've connected a resistor to limit the current so the phototransistor doesn't get too much current through it. But it's basically the same circuit I've just shown you. And let's take a look. Here is the phototransistor. It's a little transparent looking package with two leads. It's only got two leads because it's got no base connection. A collector and an emitter. The base connection is the light coming in making the electron hole pairs. And I think you saw the needle wiggle a little bit as I was playing around with it. The transistor goes into the inverting input of the op-amp, and here's the all-important feedback resistor that comes back and gives us our negative feedback and lets this whole circuit work. If I put my hand over the transistor, you can see the voltage go down. Right now, the transistor is responding to the ambient light in the room, and it is producing a significant voltage, about 3 volts at the output. And if I take a flashlight and turn on the flashlight, you can see that that voltage goes up. We don't have as much variation as we might like because we've got such intense studio lights. I could perhaps increase that by changing some of the resistor values, but there we have it. And if I were to work underneath a shade here, you probably can't see that too well, there we go. I can go all the way down towards 0 and then sneak that light in, and it goes up quite a bit. So we have a light meter. What's this good for? Well, most cameras have a light meter in them. You don't see the light meter in a modern camera, but it's in there, and it does things like calculate how long the exposure ought to be. So that's a light meter, and it uses a current to voltage converter with a phototransistor as the current source, making a current that's proportional to the intensity of the light falling on it. Well, we have seen quite a few applications in this lecture of op-amps. They're very versatile, they're wonderfully easy to analyze once you understand the op-amp rules, and we're going to go on in the next couple of lectures and look at some more applications of op-amps. If you're interested in working with such an application for yourself, I have a rather challenging project for you with this one. It's to make basically a circuit that becomes an electronic thermometer, and you've got some challenges because I want you to convert from a sensor that produces a voltage output that corresponds to Celsius temperatures, and you need to convert it to Fahrenheit. And that's a challenge because you've got to do two things. You've got to convert the size of the degrees because they're different, and you've also got to account for the fact that there's that 32-degree offset. 0 Celsius is the freezing point, but 32 Fahrenheit is the freezing point. That's a challenging project, probably the most challenging one you'll have encountered, but I urge you to try it, and there is no one right answer. But if you do that, and then we talk about the project, you'll see what the solution is. Okay, well, this is a pretty challenging project. You've now got a fairly sophisticated understanding of op amps and what they can do. So your project is this. You're building an electronic thermometer, and you have a temperature sensor that produces an output voltage whose value in millivolts is equal to the temperature in Celsius. So when, for example, it's 20 degrees Celsius, you get 20 millivolts. You're to design an op amp circuit with this sensor at the input, which produces an output whose value in millivolts is 100 times the temperature in Fahrenheit. That is, when it's 70 degrees outside or inside or whatever the sensor is sensing, the circuit's output should be 7,000 millivolts or 7.0 volts. And your op amp should use plus or minus 15 volt power supplies, and these are the only power sources available to you. By the way, this is a real problem. I once built an electronic thermometer before they became widely available, and I had to make exactly this conversion, and I had a switch that let you choose between Celsius and Fahrenheit. And then an optional part will be to simulate the circuit and verify its operation. So this is more of a design project. So think about it, get pencil and paper, draw the thing. It's going to take you a while. It's a bit of a challenge. Okay, so here is my solution, and I'll talk about my Circuit Lab solution, and then I'll show you the implementation also in Do Circuits. So here's what I've got. I've got an inverting amplifier with a gain of minus 18. Why minus 18? Because the difference between Celsius and Fahrenheit is a factor of 1.8. 1 Celsius degree is 1.8 Fahrenheit degrees, so we need that conversion. And so there's a gain of minus 18, and I've got another amplifier with a gain of minus 10, so together they have a gain of 180, which is going to be what we want to take those millivolts up to tenths of volts, basically. But there's also a problem, and the problem is we need that 32-degree offset between the freezing points of Celsius and Fahrenheit. So to do that, I'm going to bring in another current through another resistor. The only source I have is plus or minus 15 volts, so I've got that connected up there to my power supply. It's chosen to be a summing amplifier here, and I'm going to take the current that's flowing in through that new resistor I've added, and I'm going to make it account for that 32-degree offset, which in my scheme of things for this circuit represents 3.2 volts. So that current is 15 volts over the resistance. Why 15 over R? Because the other end of that R is connected to the summing point, the minus input, the point that's at virtual ground. So we have 15 volts across that resistor. That gets amplified by the ratio of the feedback resistor, and that is 39 kiloohms, and we want that to come out 3.2 volts. In other words, when there's no other input to this op amp, when it's 0 degrees Celsius, we want to get 3.2 volts corresponding to 32 degrees at the output. And so you work that math out, and that's where I get the 182 kiloohm resistor. So that is the way the circuit works. Let me show you it simulated in Circuit Lab because it uses a new feature. So I'm going to simulate the circuit. Here's the circuit now on the big screen. I'm going to simulate it, and I'm going to run not just a DC simulation, but a DC sweep. And a DC sweep allows you to start at one voltage and end at another voltage. So I'm going to start at 0 volts and end at 30 millivolts at the input. That corresponds to 0 degrees Celsius up to 30 degrees Celsius, which is a pretty warm temperature. So when I run the DC sweep, I get a graph that looks like a straight line. Along the bottom are the input voltages, which I'm naming V Celsius, and they're in millivolts. And so, for example, if I go over here to 10 millivolts corresponds to 10 degrees Celsius. If I look along there, that is, go along horizontally, I'll find the corresponding voltage at the output, and the output voltage is 5.000 volts. 5 volts, well, in our scheme of things, that corresponds to 50 degrees, and 50 degrees Fahrenheit is indeed the same as 10 degrees Celsius, and the same would be true anywhere along this linear scale. So you can verify that this circuit works by plotting a number of different values or simply using Circuit Lab's DC sweep. So that's what Circuit Lab does for us in this circuit, and it makes it clear that the circuit works. If we took a look in do circuits, the circuit in do circuits looks very similar, and in do circuits we can run also a DC sweep. It takes a little while, and there is our DC sweep, and we get exactly the same thing. For example, 0.01 volts, 10 millivolts corresponds to 5 volts at the output, so 10 degrees Celsius corresponds to 50 degrees Fahrenheit. That was a pretty sophisticated assignment. To work that out and get the summing amplifier to sum in the 32-degree offset. Not trivial. If you did that, pat yourself on the back for doing a really sophisticated circuit.